For homework 3, part A, we're going to be deriving the differential equations to calculate our molar holdup and our mole fractions within each tray of our distillation column. One thing to look at is that we have our column numbered from our first stage being the top, the condenser, all the way down to our reboiler being our last. So what we know for any given stage is what is going into it. From the top here is going to be our liquid from our n-1 stage, and what's leaving is going to be our liquid from stage n, or the stage that we're in. Then what's going into this is going to be our vapor from our stage n+1, so the next stage, and what's leaving is going to be our vapor from the stage we're currently in. So using this, we can create an equation for our molar holdup in each tray. So our molar holdup, our change with respect to time, is going to be equal to what's coming in. So our Vn plus 1 plus our Ln minus 1, and then what's leaving, so subtracted from our Vn, and then also subtracting our Ln. So our change in molar holdup with respect to time is equal to our vapor and liquid coming in minus our vapor and liquid coming out. Now to do our mole fractions, we have our holdup and our mole fractions all changing with time. I'm going to move this down a little bit. We have more room. Our mole change in mole fraction with respect to time. So we know we need to have what's coming in and out, but also our mole fraction itself. So for our vapors, that's going to be our y's, and our liquids, our x's. So our equation for this will end up being Vn plus 1, so the vapor coming in, multiplied by that mole fraction, Yn plus 1, plus our Vn, sorry, not Vn, plus our Ln minus 1 times our Xn minus 1, then subtracting our current vapor times current mole fraction Yn, then again subtracting our current liquid Ln times, this is times our current mole fraction of the liquid, which gives us our change in mole fraction and our change in molar holdup. But one last thing we need to do is, as you can see, this is our molar holdup and our mole fractions, so we can use the product rule to multiply this out, giving us our m times dx with respect to time plus our x times dm with respect to time is equal to what we have on the right hand side here. And that's important because we can use our initial values to calculate dm and then rearrange this equation to solve for dx later when we do the calculations in Python.